main question we have is, where does it come out of the bedrock? Where is that hole? Where's the crack where it comes out of the bedrock? And second is, how does it get from there to the springs?
It's a puzzle, and we're trying to understand how things are happening below ground where we can't really see them.
Because you have many springs on the surface, and we hypothesize that there is one major crack that transports the heat. And so that heat is just going all directions.
We haven't actually been able to pinpoint that exact place where the hot water is coming up from some kind of a crack or a fracture in the bedrock.
We find hot water at 1,000 feet. We find hot water at 100 feet. But in between, we find cold water. And so that's kind of a mystery. The goal is to find that spot, because once we find it, and we can find the crack that is underneath it, where the heat comes from, then we can pump directly from the bedrock system.
So after 3 seasons of investigation out at this site, there's some things that we're fairly confident about. One is the temperature of the water. Our hottest temperatures that we've measured is about 91 Celsius. It's just a little bit below boiling in several different locations out there, both at near the surface and deeper in the holes. We also know from geochemistry, so looking at the ratios of different elements in the thermal fluids, that the water's been quite a bit hotter than that at depth, but we haven't actually accessed those temperatures.
We know now, okay, it's a deeper circulating system, and there are these major faults going through the valley, right? And so why would the water come up only in one place? The thinking is that, okay, if there is an extensive web of cracks, it's more likely that the system is a lot bigger than we think.
What I did for the program was came up with new and cheap exploration tools. I myself work with satellite remote sensing. That means looking at the surface from satellites or from airborne platforms from the top. We used a technology called forward-looking infrared systems. And these are cameras that map the temperature of the ground and see where the area is hot.
So she is looking at those temperatures on the ground surface and correcting it for atmospheric conditions.
But what really is useful for us is when we fly our own aircrafts over this area, or we have unmanned aerial vehicles that we fly over the area, and then they can hover down pretty low. And when we put our camera systems on that and our thermal cameras on that, we can map this at very high detail. When I say very high detail, on the right is a blue, green, red photograph. It's like a camera photograph. And the left one is from the forward-looking infrared that's showing the high temperatures in yellows and whites. These are both taken from aircraft. An aircraft flying about at the height of 1 kilometer from the ground.
I do almost the same thing from below, so in the ground. So I'm using data and models in order to figure out how much heat is coming to the surface.
How we analyze the data for any area, it's not just a plug and play, that you just go, you get the data, and here you've got your results. It doesn't work like that. We say, this is the point in the ground. We have exactly the same point on the photograph, so it matches really well. That is very, very important. And to do that, we have onboard GPS systems, and also what we call a navigation system on aircrafts and on unmanned aerial systems, which tell you how much was the aircraft moving when the picture was being taken. So once we have those, every image frame, and we have thousands of image frames, when we have them corrected, we mosaic them. And when we mosaic them, we get a good, big, kind of a map product. And that map product actually is like a mosaicked, what we call orthorectified map product. And from that, we've got our data set. They are correct in their spatial location. And then from that, we derive our information.
In an ideal world, this would, of course, match up. So you get not just what's coming out of the surface, but also how did it get to the surface. And this animation shows imagery from Anupma, and the image is rotating, so you can start seeing the below ground parts, the parts that we have data for. And you see the dots with different colors indicating the amount of clay particles in the ground. And clay particles tend to reduce the amount of water that moves through the ground. Clay particles are very often present as a capping rock or a capping mechanism for geothermal systems. And so hot water that rises to the surface accumulates under these caps. If you look closely underneath the surface, you'll see a very dense clay layer where most of that hot water is kept under. But deeper down in the surface, you see more areas of clay or the presence of clay particles. You also see the boreholes that are drilled over the years. The colors indicate the temperatures. The hotter temperatures in the reds and the cooler temperatures in the blue. As you look carefully at the wells, you see that this blue layer is kind of continuous all the way across, because we haven't found exactly the place where the hot water comes up. And that is the big challenge.
As scientists, it's an interesting puzzle, it's an interesting challenge to have just a few pieces of information and trying to form a full understanding of how something is happening.
And the good thing about this is that we are using Pilgrim Hot Spring as a test case to look at low temperature geothermal resources. And this is a very data-rich area. So if we can do it right here, then in other areas where we do not have so much funding to go and do detailed investigation, this could be an exploration tool which is pretty low cost.
What we've recommended as we transfer this project to private sector is that they drill one additional temperature gradient hole in an area we haven't been able to get to due to logistical limitations.